Hey everybody, Jonathan here. In this video, I will be giving you my take on section 3.4, which is all about the chain rule. Now, in the book, the chain rule gives two forms. The chain rule is a way of finding the derivative of a composition of functions, which means you've got one function being the input to the other. Here, g is being inputted into f. And the chain rule says that if you have the derivative of f of g of x, then that's going to equal to the derivative of f applied to g of x as its input times g prime of x on the outside. And it also shows the chain rule using the famous Leibniz notation, which says if you let u be g of x and y be f of g of x, then dy dx is equal to dy du times du dx. So Leibniz notation is rather appealing because you can kind of see how dy dx here is going to equal dy dx here if you allowed some things like dy du to be treated like a fraction. It looks like a fraction, but it's not actually a fraction, though it often behaves like a fraction. That's part of why Leibniz notation is there for derivatives. Derivatives often behave like fractions. So in Leibniz notation, if you were to cancel these du's, you would just get dy dx back out. So Leibniz notation definitely has its uses, and you need to be aware of it. However, when it comes to doing the chain rule on more complicated problems, Leibniz notation gets very tedious to use. And I always use this first notation. However, that first notation, if you always think in terms of f and g's, can be a little bit annoying because you might already have a function f or a function g defined in your problem meaning something else, and then you have to worry about redefining things, which can get rather confusing. So the way I think of the chain rule is I call the function on the outside the outer function, and I call this function on the inside the inner function. And now the chain rule says that the derivative of the outer applied to the inner function is equal to the derivative of the outer applied to the inner times the derivative of the inner. It's exactly this, where f is the outer and g is the inner. And for short, since it's tedious to write outer, it just says O of I of x's derivative is O prime of I of x times I prime of x. And this makes it a lot easier to calculate derivatives almost in your head, or at least on the fly, without having to write out a bunch of extra steps. So for example, if we let f of x equal x squared times sine of tangent x, and we want to find f prime of x, well, first off, using this, if we only had the definition in terms of f and g's, that would already be annoying because I've defined f to be something else. F is the whole thing. It can't just be part of it. And what I do is, just like I did for the product and quotient rules, is that if you just abstractly take the derivatives without actually calculating anything, you can break it down until there's only simple derivatives and we know all of them, and then we can write in what they are. So first off, this is x squared times a sine of tangent x, which means I want to use the product rule on the x squared and on the sine of tangent x. So when I abstractly do the product rule, I get that f prime of x is going to be x squared times the derivative of sine of tangent x, whatever that turns out to be, plus the derivative of x squared times sine of tangent of x. Now I can just use the chain rule on this sine of tangent of x, on this sine of tangent of x part. I can't just get the one part highlighted, but that's okay. So by the chain rule, the outer function is sine, so it's going to be sine prime times tangent of x, because that was the inner function, times the derivative of the inner function. And just so I calculate all derivatives at once, I still haven't calculated the derivative of x squared over here, and everything else stayed the same. And now I can go ahead and fill in what all these derivatives are. X squared, because it's just copied from the line above, the derivative of sine is cosine. It still gets input the tangent of x, because that's what the chain rule says. The derivative of tangent x is secant squared x. And then finally, the derivative of x squared is 2x, so we get plus 2x sine of tangent x. This would have been really tedious to do with Leibniz notation. Not really tedious, but a little tedious, because you would have had to have this separate problem. You would have been like, well, what if y is sine of tangent of x? And then you could use Leibniz notation on just that part, and then plug it into the overall thing. But that would be annoying if there was already another definition of y floating around and things like that. And one final note is a lot of students confuse composition with multiplication. They'll see something like sine of tangent of x, and they'll think, oh, that's sine times tangent. But it is not sine times tangent. The parentheses in this case indicate the input to a function. If I did want to multiply a sine function times a tangent function, I would have written sine x tangent x. So watch out for that. Bye now.